and welcome to Chapter 1 of Chemistry 1105 at College of DuPage. I am your instructor, Dr. Corey DiCarlo, and I will be narrating this lecture. The PowerPoint slides are available on Blackboard if you want to pick up the slides as they are before they are annotated. And as always, feel free to contact me through email at dicarloc@cod.edu at any point when you have any questions. What I will be using is I actually have a high-resolution stylus pad, so I will at times be able to write on the screen. I haven't actually used this pad for a little bit of time, so if you happen to see that my penmanship is not the best in the world, that's partly because my penmanship just isn't the best in the world, and I'm working on that. And it's partly because I'm getting used to the stylus and the cursor again. So here we go. Now your book opens up the idea of chemistry with the idea that there is all of these incredible transformations occurring all around you and all around in the world. And what chemistry tries to do, in one definition of chemistry at least, is look at how the microscopic world of atoms and molecules and these little tiny particles that make up everything that's matter in the world, how that leads to these macroscopic events and properties that we see. So when we see fire, for instance, we see this little picture over here, and we see this big flame, and we understand in kind of an intuitive way that these sticks down at the bottom are burning. They're doing something, they're changing, and they're changing actually into gas, right? They're changing into all this energy being released and light and heat, but they're also being changed into a gas. And that gas is carbon dioxide and actually a little bit of water vapor. Now, when that happens, the sticks have a certain set of properties that they have because they're sticks. They're solid. They are kind of flexy and bendy. My kids like to chase each other around the yard with them for some bizarre reason, but they're sticks. But when they're carbon dioxide and water vapor, now they're a gas. You can't pick them up with your hands. They're not solid anymore. They have a whole different set of properties. And so one thing that we can think of in terms of the definition of chemistry is this is the investigation of change from one substance to another. And what this means is that you're actually changing what something is from one set of properties, like stick properties, to another set of properties, carbon dioxide and water properties. And as you start to think about this, you start to think about, excuse me, you start to think about why would I care about investigating these changes and these bits of knowledge in the universe that we can kind of look at with this? Well, I'm going to try and convince you, definitely the first day with a worksheet that we have, that one of the reasons is you want to be able to understand science well enough to know when someone's fooling you with science. That's always one issue. But the other is just that it's kind of a fascinating thing that we can actually understand these transformations, which on the surface you kind of take for granted that sticks will turn into gas if you light them on fire. But there's so much more to it than that. And so it's kind of just a fascinating science all on its own. At least that's what I'm going to try and convince you of over the course of the semester. Now, one of the key issues of this is that the models that we have come up with to describe what's actually going on a subvisible scale are all things that are happening on a subvisible scale. When I have sugar and I pour it into coffee, for instance, there's all these little molecules of sugar, which are all these little tiny atoms connected in a certain way to make up the properties that we think of when we think of sugar. That's sweet, that's a white crystal, all of those kind of things. Yet there's no way we can actually see those molecules. Our eyes just can't discriminate at that kind of a scale. So what we have to do is we have to look at these reasons in the models that we use for what all of these different substances look like on a microscopic scale. But all of our investigations happen on a macroscopic scale, one that we can actually see. So kind of that disjunction between what we can and we can't see and interpreting things based on what we can't see, but having to explain what we can, is one of the harder parts of chemistry. With physics, you throw something in the air, you watch it come back down, you try and explain that gravity is pushing it up, or is pulling it back down when your hand pushes it up, I should say. And that's something very visible and very tangible that you can get your hands on. You can hold that ball and you can throw it. With chemistry, it's a little bit more difficult in that you can't grab a molecule. You can't pull atoms apart and put them back together in a different way. So we have to kind of keep that in mind, that it's going to be a little bit disconnected in that sort of way. So in order to really get to how we understand chemistry, we have to look at how we understand science. And to do that, we look at something we refer to as the scientific method. And you'll be using this in your worksheet as you work through this on the first day of class. What you really see here is you see a set kind of process, a little flow chart over here. There's my cursor. That really starts off with an observation. People don't start out with a guess of how the universe works until they actually have some sort of visual or perceptive or hearing or some sort of way to observe something happening that makes them wonder why something is happening that way. And if you see a fire burning and there's light given off and the sticks disappear as they turn into gas, that could lead you to the question that when I observe this chemical change happening, this fire event happening, what's going on? And when you guess what it is, you have some idea that you form. Guess. You have this idea slash guess of what's going on, and you put that into words, and you put it into words in such a way that you can test your idea or your guess of what's going on. And when you can do that, you've formed a hypothesis. Okay? So one thing I could say is I think that as I burn the sticks, they turn into stick gas. It's actually still stick for whatever reason, but that's a gas. And if I cool it back down, they'll turn back into sticks again. Just like if you heat water up, you cool it back down, you can boil water off, and then you can condense it back again, and it drips back down. Or you can melt an ice cube, and you can put it back in the freezer. It's just still water, no matter what's happened there. So maybe my hypothesis is that sticks are the same sort of thing, and that's why they disappear when I burn them. Maybe they reappear somewhere else, and I'm just not seeing it. So I have this hypothesis. Now I have to come up with some way to test this craziness. So how could I test that sticks are actually just evaporating when I burn them? Okay, so well, I have to devise some sort of experiment or test. And one test could be is maybe I could burn a small piece of stick. And I could burn this inside of a sealed system. And the sealed system will allow me to make sure that none of that stick gas escapes. So when I cool it back down, my expectation is that I'm going to see that stick reform in some way. Even if it's maybe just chunks or powder or something like that, it should reform. If my hypothesis turns out to be a correct hypothesis, a correct guess or idea. So I run the experiment. I test it. What you're actually going to see, and this chart doesn't do a very good job of showing that actually. It's the book's chart, so I'm trying to use it and explain it. But you want to draw an extra little arrow here is that when you run an experiment, what you're really going to do is you're going to find another observation. You're going to see, what did I see when I ran this experiment with this sealed system and burned a small part of the stick? And what I saw was, after it was done, none of the stick returned. So whatever happened was a one-directional process, or at least it seems to be. I can't get it to reappear again like I could with water. So that means my hypothesis is wrong. It wasn't invalid to come up with that guess. but it just happens to not be the correct uh, explanation or idea for that particular system. So then maybe I come up with another hypothesis that when I burn the stick, that there's actually some sort of transformation going on to where that stick turns into something completely different. And then I have to figure out some way to test that. Now this whole process goes around and around, and goes around and around until eventually, with enough correct hypotheses, enough correct ideas to explain observations, enough, then you can eventually come up with a theory. And this is more of an overall, larger, bigger framed sort of set of ideas that all are trying to explain the same thing. And when you have that big set of theories, you can use that to try and explain other observations, come up with more hypotheses, to try and figure out more of how something works. But now you already have a pretty good set of valid and correct hypotheses that are allowing you to really understand what's going on. If huge amounts of data and huge amounts of observations all correspond to a whole set of theories and all correspond to a large set of correct theories, then eventually what we can get to is we can get to a law, which is something that we see as being pretty invariable and very well understood and explained in terms of how the hypotheses are correct that go along with the observations that we see. And if we have a law, that means that we're pretty sure that what we're explaining is really happening in the way that we think it does. Now, it doesn't mean, and this is the thing about science that's kind of different than any other investigation, any experiment that we run that we can repeat and that we can verify the results of that is contrary to what our theory thinks, or contrary to what we have written as a law of nature, or a law of some sort of scientific process. If something contradicts that, then we have to figure out what went wrong and start over with that part of the explanation. We're going to need new hypotheses to try and explain again what the deviation is that we've just discovered. So, I mean, it may be a law for us that every morning the sun comes up and it rises in the east and sets in the west, and that's just the law of how the sun works around in our universe and how it looks from our planet. But if one morning we wake up and it rose on the west side and set in the east side, we'd have to sit down and come up with new hypotheses about how the sun works and how the universe works and how our planet works and its relationship with the sun, to try and explain how every great rare once in a while the sun comes up on the wrong side. If that happens, we adjust. We don't stick to something, we just adjust as long as we can experimentally show that something's happening. Now, there's some terminology here that we have to be sure about. And that's when we talk about a hypothesis, we can be talking about an invalid hypothesis and an incorrect hypothesis. And those do not mean the same thing. Incorrect means that the test has evidence that shows that we are wrong about what we're thinking in terms of explaining a set of observations, explaining what we've seen. Invalid means that we've come up with a hypothesis that's not testable. An invalid hypothesis is pretty useless for science, honestly. Because if you can't test it, then what's the good of it? What's the point of it in terms of figuring out how the universe really works? Okay? This doesn't mean that everything in existence and everything in your life has to be testable. We're just talking about when you're working your way through a scientific study of a subject, you want to be working with something that you can test. Okay? It's actually fairly hard a lot of times to come up with an invalid hypothesis. One for our stick example could be that when I burn sticks, invisible stick fairies, that there are no way, something that we can detect, come by and steal the sticks when we're not looking. Alright, well, if they're undetectable, invisible stick fairies, I'll never be able to catch them because they're unobservable, they're invisible, I can't see them. So there's no way to test whether that's really going on. I mean, it could be, for some bizarre reason that just seems like they burn and turn chemically into something else, but the stick fairies happens to be true. But it doesn't matter if we can't test it because we'll never know whether it's true or not. We can't disprove it and we can't prove it. And if that's the case, it's an invalid hypothesis. Okay? So we continue down this little pathway, and even what we're going to talk about a little later, John Dalton's theory of atoms is really just a long investigated and well explained set of hypotheses about how observed changes in substances work. And so all this atomic theory that we're going to talk about later is just the end product of exactly this sort of process. Just happened before. And so let's give ourselves a problem here. And feel free to pause at this point, think about it, write out your answer. But we're going to look at this idea that some newly discovered extract of some magical sounding berry grown in Southeast Asia is being claimed to cure malaria. Okay? So how can we classify this claim? Someone's saying this can cure malaria. Is this a fact? Is it something we know? Is it a theory? Is it a hypothesis? Is this a myth? Let's pause it. Think about it. Okay. This is a hypothesis. Okay. This is someone's idea of what's going on. Does this berry really cure malaria? Was it a coincidence? Did the person was the person actually cured? There's no experimentation having occurred yet. All we're saying is, hey, look, we found this berry, it cures malaria. So that's the idea that these people have. If they start offering experiments with results, and more experiments and more results, we can then say that they are correct hypotheses and that we are believing them. And then if we come up with a whole overarching idea of how this particular set of berries and this particular set of compounds all combine in our knowledge set to form a larger idea of how this all works to maybe actually cure malaria, that larger set of explained hypotheses would eventually become a theory. Now, when we talk about matter, we're going to have to get through a few definitions here. And I know the first couple of chapters are going to be kind of chock full of, oh, I have to memorize this because it's new language. But there's no real way around that. It's a new subject for some people. We have to have a new terminology to describe it. So what we're looking at is changes in matter. Right? And our definition of matter is anything that takes up space. If it occupies space, it's matter. It's stuff. Okay? So matter, it's almost harder to think of something that isn't matter, right? One thing you can think of that isn't matter would be perhaps energy, light, sound waves traveling through space, heat. All of these things are not matter. And matter, anything you can touch, feel, grab a hold of, takes up some space somewhere. Now, we split these up into two different basic categories. Pure substances, which are made up of elements, which we'll talk about a little bit more later, and compounds, which are basically just elements bonded together in very specific ratios. The other possibility, instead of a pure substance, we could have a mixture of pure substances. So we could have a soft drink, for instance, some sugar, some water, some color, some carbonation, some caffeine. All those things by themselves are pure compounds, but when you mix them all together, you have a mixture. Okay? Now, there's two types of mixtures. We have a homogeneous mixture, where you look at it and you say, wow, this all looks pretty much the same. All of the soft drink in there, I mean, not the ice, but just the soft drink, pretty much all evenly mixed. I can't discern any individual small portions of this. That's a homogeneous mixture, one where I cannot discern individual different regions from one part to another. A heterogeneous mixture is one where you can very easily, or at least in some way, see that there are different portions to this thing that you've tried to mix together. So oil and water, for instance, is an example of a heterogeneous mixture where you can see the oil, you can see the water. Even if you shake them together, you're going to see droplets of the two not mixing. So in one section of the cup or container, you have more oil and less water. Another section, you might have less oil and more water. It's not uniform. So that's one way you can think of these different things, is uniform or not uniform in terms of mixtures. So a pure substance. Let's talk about elements a little bit more closely. An element is an item that you can't break up into things that are chemically different. So if you have an element, if you have some sort of substance that you're sitting there in front of and you can't heat it and make it turn into something simpler and break apart, you can't use electricity to break it apart, you can't blast it with laser light and make it into something simpler, into smaller pieces that have different chemical properties, then that's an element. What are examples of elements? Well, just open up your periodic table at the front of the book. Every one of those substances on the periodic table is an element. Something that can't be really broken down into smaller pieces that still have that same set of properties. Now, compounds are just what happen when you take a couple elements, a couple of these elements, hydrogen, oxygen, what have you, and you combine them and bind them together in a way that doesn't break apart easily. So if you wanted to, you could find a way to break apart a molecule that might be composed of an oxygen and some hydrogens. And if you, say, zap this with electricity, you could break it down into simpler units. You could break it down into just the element oxygen, and on another side, just the element hydrogen. And you could separate those pieces. But unless you do something like that, they're going to float around and they're going to stay as just water molecules with two hydrogen atoms connected to an oxygen atom as a unit, an overall unit that acts like water. So there's some definite proportions here, some definite ratios of individual elements, and that's what makes up a compound. So now mixtures, you have two or more pure substances or two or more elements, they're mixed together in some way. Now, as we said before, homogeneous means it has the same composition throughout. So air, it's a little dicey. Air can be a little different from one place to another, so it may not be actually a homogeneous mixture, but what they're talking about is if I just kind of grab this one small portion of air, everywhere in that little box I've drawn more than likely is completely evenly mixed throughout. Okay? However, if we look at things like salt water, you could have some sand mixed in there, you could have a fish here and there. That's not going to be completely homogeneous throughout. If I grab one little portion of salt water here, I get some salt water. If I grab some deeper water over here, I get some sand and salt water. If I grab this portion, we get the shark that's waiting to catch this guy as soon as he's not looking. So these are not even mixtures. There's different compositions in different areas. Alright, so let's figure this out. What are these different things? We have 14 karat gold ring, we have sand, we have carbon dioxide, we have diamond. Are these things elements, compounds, mixtures? What are they? Okay. Pause it, write down your answers, think about it, and we go on. Okay. 24 karat gold is actually pure stuff. That's how they work this in the jewelry industry. Anything less than that means that they've mixed it with something else. And it makes it a little cheaper. Sometimes it makes it a little more rigid so it doesn't bend or dent as easily. But that's how it is. However, when they do this, they mix them together in such a way that you actually have a solid mixture of metals. So that's completely homogeneous. No matter where you grab a chunk of this 14 karat gold, it's going to be that same ratio of copper and gold and nickel. And now, sand, even though it looks kind of uniform, Sand is actually a heterogeneous mixture. It means that we have some quartz, that's the bulk of the sand. We have some minerals, some other little rocks, some seashells, maybe some salt from the salt water. All of that stuff mixes in, and it's different. Each handful of sand that you grab is a different ratio of those different things. So that difference makes it heterogeneous. Okay, so carbon dioxide is just some carbon, some oxygen, smush them together, hold them together with bonded, some nice bonds between the carbons and the oxygens. That's going to be a pure compound. It has two elements. It has oxygen and it has carbon, but it's a pure compound in that all of the carbon dioxide that you find will be the same as any other carbon dioxide that you find somewhere else. Now, diamond is actually just carbon. It's the same element as coal. It's just in a slightly different form, but all it is carbon. There's no other elements involved in that, so that makes it a pure substance. Specifically, it's an element, pure substance. Now, the states of matter, and we'll get into a little bit more of a microscopic definition later. And, you know, they do this in the book, so I mention it because I want you guys to know it, and I don't want you to be fooled by the homework. But very few people are fooled into thinking a solid is a liquid or a gas is a liquid. These are pretty no-brainer type things. If you have a solid, you can't smush it. You have rocks, you have those sort of things. You can't compress rocks and that sort of thing into a smaller shape. It has whatever volume it's going to have. You can mush it, you can, like Play-Doh, you can kind of smash it down and it spreads out, but you're not going to make it into a smaller overall total shape. If there's air gaps inside of it, then you can get rid of the air gaps. But the solid itself is going to be an incompressible thing. It has a very specific volume. Solids don't expand or contract, and it's going to have whatever shape it's in. That's the shape that that solid's going to be. It's not going to flow like water does. It's not going to float away like gas does. Now, liquids are incompressible too, and that may not be obvious, but if you have a cup full of water and you put a lid in that water so that the water can't escape, and you push down on it and you try and squish that water in tighter together, it's not going to happen. And you can't compress water any tighter than it really already is, at least not in any reasonable way. The volume, again, is fixed. It's not like a liquid spreads out or shrinks in just all by itself. You can do that with temperature, but that's not what they're talking about here. But there's a variable shape, meaning what they're talking about here is that if you put it into a square cup, liquid's going to be square. If you put it into a round cup, the liquid's going to be round. That's all they're talking about. Gases are compressible. You can force a bunch more gas in and squish it in and make it a lot more dense gas. You can open it up to the air and let it disperse, and that gas will take up a lot more room but be a lot less dense and concentrated. So that means what it means by compressible. You can concentrate it, you can make it less concentrated. And because you can do that, the amount of space it takes up can vary. I can have the same amount of gas in a small little container of perfume. I open it up and the perfume, all of that, it spreads out throughout the room, and the gas that used to be at the little head space of the liquid over the perfume in the perfume bottle is now hugely spread out through the whole room, giving it a much larger volume. The shape pretty much takes on whatever shape that the environment has. It'll take on the shape of the room or the house or whatever the container needs to fill up. Now, when we look at these different parts of matter, what we actually see on a molecular scale, on the little bits of elements attached to each other, is that in a solid, one of these molecules, these units of atoms, are connected to another, and to another, and to another, in a grid that can't be broken up. This grid is going to stay intact, and that's why the solid maintains its shape. In a liquid, the different little molecules of water, for instance, are attracted to each other, so they're kind of sticky and they stick to each other. So they can't fly away and float away like they could if they were a gas or they evaporated. But they're not rigidly held together one to the next. So they just kind of slide around each other and next to each other. And that's why liquids kind of slide and flow. Now a gas, they have no attraction to each other. So they just fly around wherever they want to and bump into things and fly off to a new direction. And that's why they have the properties that they do, is that there's just no attraction from one water to another unit of water once it's a gas. Alright, so what's a grape juice? A cup of grape juice. What's its state? What's its composition? Take a moment, pause it, and we go on. Well, at room temperature, that cup of grape juice is going to be a liquid. Stick it in the freezer, it's going to turn into a popsicle. It'll be solid. What's its composition? Well, it's uniform. It's, we have some color in there, we have some sugar, we have some flavor, so there's more than one compound. Not a pure compound, because there's more than one thing in it. But we do know that we can't see in a glass of grape juice, at least, and that may not be true of like pulp or something like that in a different type of juice, but grape juice, we can't see any different regions, anything that's different from one part of the cup of juice to another. So that means it's a homogeneous solution, a homogeneous mixture. So there's two sets of things we want to look at now, because when we look at things changing, what can happen can be confusing. When I burn a stick, it's gone. It's turned into something totally different, carbon dioxide and oxygen. When I heat up water, it's still water. It's water gas now instead of water solid or water liquid. So we have to differentiate between those two ideas. Physical properties. These are properties that you can have for a substance, and properties that can change. And when they do, it's still whatever it was. So if I'm looking at something and I see that it's a solid, and I see that it's red, and nothing is happening at that moment to it, it just is those things. That's a physical property of that substance. Color, shape, all those types of things. Now a chemical property, chemical changes, which we'll talk about, those are these properties that you can see only when something's changing into something else. It's flammable. It burns. When it burns, it's turned into something else. But the only way we can see this chemical property of being able to burn is by having that occur. Okay, so it has to change its composition in order to see that particular property. Okay, so this isn't easy. There's a reversibility aspect to this that tells you whether it's physical or chemical. When I cook an egg, for instance, is that a physical or a chemical change? It goes from liquid to solid, right? But when I cool it back down, that egg doesn't turn back into a liquid. So since it's not really reversible like ice and water vapor are, that's a chemical change. If I evaporate alcohol from a container of rubbing alcohol, for instance, I can cool that gas back down. It'll turn right back into rubbing alcohol. That's a physical change. So let's look at these changes. And keep in mind, can I reverse them just with something simple like temperature? Will they go back to exactly the way they are, just using temperature in some way? So you're paused. Now we go on. So rusting, you take a piece of iron and it rusts. You can heat that up, cool it back down. It's not going to turn back into iron anymore. It's going to be rust. It's going to have the properties of rust, which is flaky and powdery, instead of the properties of iron, which are metallic and stays intact and together. That's a chemical change. It's changed and it won't change back. If I dissolve some sugar in water, it may not be obvious, but if I heat up the water and evaporate it out, I can collect the water again as just water, and the sugar will get left behind as a powder in the pan that I evaporated the water out of. It didn't actually turn into something different. All they did really was mix. So mixing together, nothing changed what it was. They just mixed. That's a physical change. All right, if I burn paper, if I cool that back down, am I going to get the paper back? That means that paper burning, chemical change. Ice melting. Well, this was one of our main examples, right? Ice melts, it's now liquid water. Doesn't mean it's not water anymore. If I cool it back up, it goes right back to ice. So that's a physical change. Nothing changes its chemical set of properties. It doesn't change the substance that it is when it changes in some way visibly. All right. So we had a couple of different laws that came from a whole series of observations that led to all sorts of experiments, that led to all sorts of theories that were found to be correct and repeatable and verifiable and useful for predictions, until eventually we have some laws. Okay? First law is the law of conservation of mass. And all of these things are what went into coming up with the idea that there are these little tiny bits of matter called atoms that are really the building blocks of everything that we use, and that what chemical reactions actually are just a rearrangement of how those different atoms are connected to each other. But they didn't know that. So they had to kind of look at the observables and build up to that idea. So the law of conservation of mass says is that matter isn't created or destroyed when there's a chemical change that happens. Right? Because that's what people noticed. If they weigh how much I have at the beginning of a reaction, and say I have 10 pounds of something, and I react it, I burn it, I change it in some way, and I collect all of the pieces that come off of that change, all of the gas that came from burning the sticks, all of the ash that's left over after the sticks have been burned. I weigh all that up together, and it may look different, and it may have different properties, but I still got 10 pounds of stuff. So I didn't get rid of anything, I didn't make anything. All I did is make it into a different form. So this is what really came up with the beginning of this idea of chemistry, of studying the changes that happen. And this was really made possible by being able to look at burning things basically inside of closed containers. Now, through another set of experiments, Proust has come up with another law that was really fundamental to understanding that things are made up of little units that just rearrange how they're attached to each other. And that's the law of constant composition. And this idea is that if you have a sample of something, like water, that water is going to have the same proportion of whatever elements make it up, no matter where I find it. So 1 pound of water, for instance, or 1 pound of hydrogen in a sample of water, hydrogen, there we go. Chemist, I have to be able to spell the element names. 1 pound of hydrogen, and if I have this 1 pound of hydrogen, I'll actually have 4 pounds, or I'm sorry, 8. Let me try the little magic eraser here. Oh goodness, don't do anything bad to the presentation. I actually have 8 pounds of oxygen. And that ratio, that 1 to 8 weight or mass ratio of hydrogen to oxygen, is there in every single bit of water in the entire universe. If it doesn't have that ratio, it's not going to act like water. So finding this out, that you always get these specific ratios for specific compounds, helped kind of cement the idea that these things must be made up of the same parts. And those parts must have individual units that you can't just break up infinitely into smaller and smaller halves. Because if you could, then you wouldn't have these constant proportions. Okay? So here's a little idea that we can kind of look at. Oxygen and hydrogen combining this 8-to-1 ratio to form water. And we actually know now that's because 2 hydrogen atoms and 1 oxygen atom combine, and these little atoms actually weigh different amounts. Oxygen weighs more than hydrogen does, so that's what gives us this ratio. Now, hydrogen peroxide, which has a different set of properties, you can't drink that, that'll kill you. It has 2 hydrogens and 2 oxygens. So that means that we're actually going to get a different ratio. And when we measure out what we find, is we get about 2 grams of hydrogen to every 32 grams of oxygen. So what's the mass ratio of oxygen to hydrogen in this hydrogen peroxide? And all we look at is, okay, 32 grams of oxygen, and what's the ratio of that to hydrogen? Well, I said we had 2 grams of hydrogen. So that means that we actually have a 16 to 1 ratio. Different than the 8 to 1, right? And why? Well, we have twice as much oxygen. And so this combining oxygen to hydrogen mass ratio for water, it's different. Is this an observation? Is this consistent with the law of constant composition? Yes. Because now we're seeing things even that are slightly different ratios, but they're proportional ratios. I add an extra oxygen to something, and now instead of 8 to 1, I have 16 to 1. That's the kind of thing that indicates that you must have added a unit of oxygen in there somewhere. And that unit turns out to be what we call atoms. And here's this great long explanation that basically says what I just did. And so Dalton's atomic theory is that all matter, all stuff that takes up space, is made up of little particles that we're going to call atoms. And another part of his theory is that all atoms of a given element are alike. So all hydrogens are like all other hydrogens, all oxygens are like all other oxygens. This part of his theory had some contradictions later on, after his time. So there's some slight modifications that we'll have to make to this to understand the more modern view of the atom. But for Dalton's theory, and for most intents and purposes, this statement is perfectly fine that all hydrogens are exactly the same, all oxygens are exactly the same as any other oxygen. Now the atoms are different for each element. So hydrogen is different than oxygen, oxygen is different than carbon, even though all the individual carbons might be the same as each other. And then, with all of these two laws of constant proportion and constant composition and constant mass, these kind of combine to the idea that these atoms of the different elements are just combining with each other and bonding in some sort of way. So if they just bond together, they're doing this in some whole number ratio, meaning that these atoms aren't splittable. I'm not adding half an atom of hydrogen to something. All I can add is one atom of hydrogen to something. And that must be what's leading to these constant mass ratios that we see experimentally. And so this is a theory that's based off a huge amount of information that Dalton had at the time. It has proved out to be pretty much exactly correct according to everything that we've found since, with, I said, mostly a couple of modifications here about that all elements are exactly identical to each other. So now to get a little bit more information about how this atom is really put together, we have Rutherford's gold foil experiment. And this is kind of an interesting experiment where we have a little thin sheet of gold foil. We're going to shoot something that they found called alpha particles, which they knew were pretty big, dense particles that get shot out of a radioactive material. And you can focus them by blocking them off except for one direction with lead. So it flies into this piece of gold. Originally, they thought that these atoms were made up of some different particles, and that you basically had this kind of nebulous cloud, and you had some negativity in this cloud kind of uniformly put around, and then you had some positivity uniformly distributed around too, and that they kind of merged all together in kind of a big pudding-esque kind of form, where everything was basically even density all the way throughout. And if that was the case, then when you shot this big solid chunk of alpha particle at the gold foil, their thought was it should just punch right through. It's not going to be deflected. It's not going to be hindered in any way by the foil. It'll just blast right through the foil atoms and continue on and be detected on this little sheet of detector material on the other side. When they actually ran this experiment, it bounced. You had most of them went through, but some of them bounced off of the atoms. Some of them deflected off the atoms. And if they were just nebulous clouds of positive and negative material, that couldn't happen. That couldn't be. So what this had to show is that the actual particles, most of the particle is actually, instead of nebulous cloud of positives and negatives, is actually more like a very dense, I don't know why it's doing that, there you go, a very dense center, and where the positivity is, and then around that, in very discrete spaces with nothing between the two parts, the negative portion is located. Okay? So almost all of the mass, all of the big chunk of the atom is all in the center. And if that's the case, then the deflection that we're seeing of the alpha particles is whenever I hit that dense center, bing, pops off and goes a different direction. Or if I have a glancing hit, then it goes off in a different direction. But if I miss that dense center, it goes through. So that's the theory that had to develop that was different than the original, this kind of plum pudding-esque theory of what the atom looked like. Had to be modified to account for this experiment, and the modification is that we have a dense center. Alright, so the whole thing was neutral. So the positives and the negatives had to even out. We have to have the same number of positive particles as negative particles. We call the positive particles protons. We call the negative parts electrons. And inside the nucleus, there's actually some other particles called neutrons. Those were discovered a little later. But most of the volume of this atom, if they look at the size of the atom and the density of that center, and the tiny little bits of negative material that float around on the outside, this whole thing is mostly empty space. And how much kind of empty space? Well, let's do a little thought experiment here. If I take the center, the nucleus, what the center of the atom is referred to, and I make it, I don't know, let's make it about this big. So on your screen, it might be the size of, well, if you're looking at it on a phone, it's small. But let's say this whole thing is the size of a beach ball. Okay, and this beach ball is the nucleus. Okay? And this is where all the protons are, the little positive parts. All the neutrons are, which don't have positive or negative aspect to them, they just have mass. They're all in that dense center. Okay? If I made this nucleus this big, the electrons can't make a circle because it thinks I want to do something else. But electrons, there we go, right about there, would be about that big, about 2,000 times smaller than the beach ball. So if I made a nucleus this size, there's the electrons. So how much empty space is in between here and there? Make a guess. Do you think if I put this beach ball at the front of the classroom, for instance, in our class, and I set it there on the countertop, would the electron be at the back of the room if this was our scale? It'd actually be farther. Alright, would it be in the next classroom? Nope, it's still farther. Would it still be on COD's campus at least? Nope, it still wouldn't be on COD's campus. In fact, the electron wouldn't even be in Illinois if we made this model proportional to the actual size of an atom to scale, with the neutron the size of a beach ball, the electron the size of this little dot. We'd have to put the beach ball nucleus on the desk in the classroom and the electron somewhere in the middle of Texas to represent the scaled space between those two objects. So there's this huge amount of empty space. In fact, the universe is mostly empty space with these little blips of matter here and there that make up atoms. Alright, so if we kind of look at the aspect of this, we can look at a material like graphite. That's what's in the pencil tip. It used to be lead. It's not lead anymore, but now it's made up of carbon atoms in a material called graphite. And so those little individual atoms are solid, so they're all kind of rigidly held in the structure together in this nice set of material that forms into a point, and that's our element carbon, and we're using it in a pencil. If we zoom in on one atom, we have this really dense nucleus, huge amount of open space, which we can't really represent well, so we're just going to say it's a little closer, just so we can actually show it in the same frame, without having to go to Texas. But we have this really diffuse cloud of electrons. And it's very small particles all around it. So those carbons are there, but the nucleus, empty space, diffuse electrons. And then the neutrons, those neutral objects, and the protons in the nucleus are really close together. There's almost no space at all between them. So this is our view. This is our view of the atom. So let's think about this. If we have a neutral carbon, that means it doesn't have a net positive or negative charge to it, that particular atom. And it has 6 electrons outside the nucleus that we can detect somehow. How many positive protons must we have in there? And I'll tell you this. 1 electron is as negative as 1 proton is positive. And here's our little symbology that you'll see is a lowercase e with a negative superscript. That's an electron. That's how we're going to refer to electrons. Conversely, protons, P with a plus, those are protons. That's how we refer to those. And if they're equal in charge, not in size, but in charge, and I have 6 electrons on the outside of the nucleus, how many protons are in the center of the nucleus? What other particles inside parts of an atom would be in the nucleus other than the protons? So you pause it, write it down, you think about it, we go on. If it's neutral, meaning that there's no unequalness of plus and negatives, 6 electrons means that there's 6 protons. Otherwise, it won't be balanced and the whole thing will be slightly positive or negative. If you have an atom, the other thing you can find in there are neutrons. We represent that by an N with a 0 superscript next to it. That's our neutron symbology. Okay? So this chapter is finally over. Hopefully you didn't just read through it all in one sitting and you got to see this in a couple of sittings. But if you didn't, I'm sorry. This is what we do. I would recommend for future chapters you kind of break it up, or if you like to binge on information, go ahead and go through the whole thing at once. Don't forget you need to have video notes for this, and that those video notes will have to be brought into our second class. Normally you would be reading this before the first class, but I can't reasonably expect you to have seen these videos before you come to class on Monday, first time you even know you have to do this sort of thing. Thank you for watching.